From the Oregon State University Extension Service, this is Pollination, a podcast that tells the stories of researchers, land managers, and concerned citizens making bold strides to improve the health of pollinators. I'm your host, Dr. Adoni Melathopoulos, Assistant Professor in Pollinator Health in the Department of Horticulture.
Oh, faithful listener, thank you so much for sticking with the podcast. It has been a particularly busy but very productive time here at the OSU Pollinator Health Lab. Lots of great research we've been up to, but in the midst of it all, I've carried my handy field recorder with me everywhere I've gone, and I've got a whole hopper of podcasts ready to release from Georgia to southern Alberta, to Hood River, where we talked with somebody who's restoring water pipeline that's been buried to pollinator habitat, to just down the street. There's a school that has integrated mason bees and honeybees into their curricula. So lots of great episodes to come, including today's episode. You know, a story is very cool when multiple people send it to you in your inbox. And you can always do that. If some story comes across you're interested in, send it to me and I'll follow it up and track it down. But this story happened right here at Oregon State University, just down the street, under my nose. I didn't even know about it. Corey Simon, who's an assistant professor of chemical engineering, and Hiao Li Fern, an associate professor of computer science, oversaw this great project on using machine learning to try and predict the toxicity of pesticides to bees. And today I've got the lead author on the paper, Ping Yang, who's a graduate student here at Oregon State University, and Adrian Henle, who is a doctoral student in chemical engineering. So without further ado, let's dive into this whole question of whether you can train a machine to look at molecules and predict whether it's toxic to bees, this week on Pollination. I'm so excited today to welcome Adrian and Ping to Pollination. Welcome, Adrian.
Hey, thanks for having me.
And welcome, Ping.
Yeah, hello, this is Ping.
So I guess just to begin with, this is an intriguing paper. I was really excited to have a number of people refer it to me. And so maybe just to start with, Ping, where did the idea, you're over a couple blocks from me in engineering. Where did the idea come from to, use machine learning and to this real specific problem of bee toxicity? How did your lab kind of develop this thought?
First of all, actually, we have developed we have a thought to use this kind of new graph kernel scenes into our machine learning method. So we do some research on this machine learning field, that we find that's a paper that interests us. And also the pesticides, we think that were very used widely in agriculture, and it has an economic means to control the weeds, the pests, and the pathogens. So we use the pesticides increase the expected crop yield and also the quality, and contribute to the food security. But we think that the widespread pesticide use has some negative externals on our ecosystem and human health. Especially, it will kill some agriculturally beneficial species, not the deliberately targeted. So, such as our main character, in our paper is bees. So we think that we can use some machine learning algorithms to speed up the prediction of thousands or hundreds or millions of the pesticides toxicity, and we can get the result very quick, and it's useful for our further research in the lab. So we develop this algorithm. And
I remember we were talking earlier that, one of the starting points was that, the Environmental Protection Agency already collects data on, acute toxicity to bees, the short-term exposure in a laboratory setting. And so the lab already had this great data set to start this machine learning process on these chemistries. So you have, maybe just let's get into the methodologies a little bit. So we've got these chemicals, and I guess maybe here's a way into this part of the conversation. People have heard about machine learning before. You know, we all know when you go into Google Photos, you can type somebody's face in and they'll find all the, clearly there's a lot of capacity, but I don't know if people often think about chemicals, like the ability, what's the data that goes into machine learning apart from the toxicity, but for any kind of broad, maybe Adrian, just give us a sense, like what is the input? What goes into the machine learning? What is it learning from?
So in our case, and in a lot of cases for chemical machine learning, what we're looking at is what's called a graph representation. So anybody who's taken high school chemistry has drawn the little diagrams where you have an atom with a line to another atom and so on. And if you consider the atoms to be nodes or vertices in a graph and the bonds to be edges of the graph, you end up with sort of a flattened out picture of the connectivity of the molecule. And so that's really what the model is learning, is A connects to B, which connects to C and back to D and so on. So you could think of it as the shape of the molecule, but it's the shape without space.
Okay, because the molecules, clearly they've got all sorts of orientation around the bonds, but this is a flattened representation, and what it has to learn from, I guess, is this data set. And I suppose that's one, you were telling me about the distinctions between different types of machine learning. Some machine learning, you kind of tell it what to look for, and in others, you just let the computer learn on its own. Tell us a little bit about the methodology that was used here.
Right. So here, what we did was the data set ultimately comes as what's called a SMILES string.
String?
SMILES, yeah.
Okay.
Looking happy. It's an acronym that somebody backronymed it together, but what it really means is it's a way to write out the structure of a molecule in text. And our code reads that in, constructs the graph representation from that string. And then for every SMILES string in the data set, there's a classification, toxic or non-toxic. And by doing a whole lot of analysis of those graph structures and learning which motifs happen more often in the toxic versus non-toxic classifications, and if you give it a new SMILES string, it'll look at the graph, think about it for a little bit and say, yeah, this is more in common with the toxic set than not. So I'm going to predict toxicity.
Okay, great. So Ping, if I get this straight, this kind of combination of the toxicity, whether it's toxic or non-toxic, and this flattened kind of chemical structure gets fed into the machine learning. What happens then, and how do you know that it's actually learning? How do you confirm that it's actually learning something meaningful?
So actually, if you put some, like Andrea said, SMILES strings into our machine learning method, it actually just compare the different the common part or both the difference and common parts. Actually, it's not parts; it's patterns in the graph, and the pattern in graph will be compared and used into because we already know some pesticides is toxic or not toxic. So we use these pesticides to get the whole things first. That we use these toxic pesticides compared with other that we don't know the toxicity things. And then if we find that very frequently showed patterns both in these pesticides, then we can somehow perfect confident that these new pesticides must be also toxic.
Okay.
This is how we compared it.
So right, so you had some knowns, and then you ran a number through, and just if it could guess them correctly, then that gave you a sense that it was really learning properly. It was not just randomly assigning it was accurate. So tell us what the results were. Was it able to learn from a molecule structure what if it's a toxic or non-toxic product?
It cannot just based on the molecular structures. We cannot definitely say that it is toxic or non-toxic. But from our learning, that it's more like comparing the. Actually, we use the word walk. We use the walk in the graph kernel. So actually, we are comparing using the walk to count all the different parts and also the common parts in between two different patterns or two different graphs.
Oh, wait. So what do you mean by walk? I know what walking is in non-engineering machine learning terms. So what does walking mean in the model?
Yeah, a walk in a graph is like you. So graphs are basically constructed by some nodes and some edges. So each are connect two nodes. So a walk is a step from one node to another node and to another. It's like a step in between the nodes.
Okay.
So that's a walk. So actually, when you do a walk, you can compare two different walk between two different patterns or two different graphs. So if you are going, like if I fly from San Francisco to Portland, and you fly from Los Angeles to San Francisco and then to Portland, then we have this common walks that called San Francisco to Portland.
Okay, and that makes sense. Okay, so it's kind of, and I imagine people who fly from that route, general route, may be more similar to the people who fly I don't know, Anchorage to Edmonton or something. It's just it might be a much different kind of group of people. And so getting back to this question, so the walking is in some ways you're walking from the atoms inwards and looking for similar walks, and that getting back to the question of can it predict toxicity, I guess it can look for similarities.
Yeah.
Okay.
Yeah. Graph kernel is actually comparing the similarity between different graphs.
Okay, so Adrian, so it seems like it can maybe it was really successful at predicting compounds that were related to one another and being able to tell if it's a toxic one or not. Did I get that right?
Yeah, that's right. Yeah, so in the data set we had about half a dozen different classifications of commonly used pesticides, fungicides, miticides, and herbicides. All things that you would want to know. If I spray this on my crops, is it going to do what I want and only what I want, or is it going to do some other things off target? And so from all of those data together, the model was able to make pretty good predictions. I think things said before, the whole data set accuracy was somewhere in the 70 to 80% range, which at first I didn't think was all that good, but we had an invited speaker last term, Professor Taylor Sparks from the University of Utah, who also runs a podcast on material science called Materialism. Great name.
That's awesome.
And a great guy, very friendly. And so we were telling him about this, and he said, 80% is actually kind of fantastic, because think about what it would take for you, a human being, to look at a few thousand potential new molecules. And could you, in a day or less, tell me with 80% accuracy if these things are going to have off-target toxicity? And the answer is absolutely not.
Yeah, I doing some of those studies here at OSU, it takes a lot of effort. You need to get the bees, you need to get them at the right stage, you need to make sure you have good laboratory practices, so it's auditable. It's a big undertaking. So this could be a great tool for kind of making quick screens of new chemistries. And it's like, we better really put our attention to this because this looks like it could be a real toxic to be kind of product.
Yeah, we see this as sort of a prioritization tool. So if you have a big database of molecules that you might want to test out for a new product, and eventually you're going to have to do this real, in vivo testing to determine toxicity. That's the slow, expensive, difficult part. The ones that the model says are almost definitely going to be toxic to the wrong thing, you probably just won't make those. Focus your attention on other things that have a better chance of being appropriately targeted.
Well, I'm glad you raised that. And I wonder, Ping, what do you see as some of the applications of this, and what are some of the next steps with this work?
For this work, actually, we not only want to test only the toxicity of pesticides. Actually, for our further research on this project, we actually want to expand the area of predictions, so we can get other things, because we can test a lot of different small molecules. We can test the similarity between different small molecules, so we can not only just do for predict the toxicity of the pesticide, but also other things like actually we are doing something we are trying to do is because we are a lab doing for some simulation of MOF, metal organic framework. So sometimes we will want to do is like the storage or the absorption of gas of different gas in the MOF. Yeah. So that's our further research. But based on the pesticides, we can do is actually to increase the accuracy of our prediction of this toxicity, because our algorithm is not that perfect to predict all different kinds of pesticides. So there is some way to increase our accuracy, I think.
Okay, so that's a next step might be to you're at 70 or 80%, but I imagine there must be other methodologies to kind of, and other products or other ways to look at these molecules that may reveal even it gets it even sharper. Wow, this is amazing. Adrian, is there anything that you wanted to add to that in terms of applications? You talked about kind of like a screening tool. Is there any other kind of ways that you envision this technology being taken up, or maybe next steps?
So, I mean, the real easy sort of lateral move on it would be, this doesn't have to be about bee toxicity. The method should work if you have some set of molecules and some property that you want to be able to predict. So, if you want to predict, are these things going to be harmful to people? Are these things going to be useful for the treatment of a specific disease or condition? These are all equally answerable questions using the method that we described in the paper. Then in terms of how to really take the technology to the next step, as you mentioned, there are a plethora of other machine learning techniques that we could either supplant ours with or use to help refine what we've done. Interpretability would be a really, really cool thing, I think, to tackle next, because right now we know how well the method works, but we don't really know why. And that's a common problem in machine learning. The model does what it does, and in the end, you have you can give the model to other people. It's a huge set of numbers all written down, and they don't mean anything to the human mind. So it would be really cool to come up with something that would look at what our model does computationally and show us, here's the thing that really mattered. Here's what I saw in the data. Because then, a human organic chemist learns really, really well that way. Here's a chunk of molecule. Do or do not put this into the next thing that you make.
Oh, I see. So, one of the things that another next step is it, because the machine learns and you don't really know why. It just tells you this is toxic. But what if you knew, there's a kind of kink in the molecule here, or this combination, and then somebody who's designing new products can make sure that they're not toxic to bees. It's like, I know to avoid that in the synthesis.
Right. Yeah. It's human beings can learn from the model that way.
Oh, fantastic. Well, this has been really wonderful talking with you both. Congratulations on your publication, and we are looking forward to hearing more about your work here over in horticulture.
All right. Well, yeah. Thank you again for having us. It's been fun.
Thank you.
Thank you so much for listening. The show is produced by Quinn, Sin, and Neil, who's a student here at OSU in the New Media Communications program, and the show wouldn't even be possible without the support of the Oregon Legislature, the Foundation for Food and Agricultural Research, and Western SARE. Show notes with links mentioned on each episode are available on the website, which is at pollinationpodcast.oregonstate.edu. I also love hearing from you, and there's several ways to connect with me. The first one is you can visit the website and leave an episode-specific comment. You can suggest a future guest or topic, or ask a question that could be featured in a future episode. But you can do the same things on Twitter, Instagram, or Facebook by visiting the Oregon Bee Project. Thanks so much for listening, and see you next week.